Hi friends, very good evening and thank you for joining in today. Could you please confirm in the chat window if you are able to see my webcam and also listen or hear to my voice clearly? Of course, I'll start sharing the screen as we progress through the session, but just wanted to get a confirmation if everything is working all right. So I'm also looking at the chat window on YouTube. So could you please confirm if everything is working as expected? That'll help us understand that there are no technical glitches and we can get started. We'll start at 7 p.m. sharp. 7 p.m. sharp. We are still 4 minutes away from it because the scheduled time is 7. So let's wait for 3-4 minutes before we get started. Hi folks, thank you for joining in and a very good evening to everyone who joined a little early. I and some of our team members have been answering a few of the questions in the chat window in the last few minutes. Again, thank you everyone. Welcome to this session. As I was just saying, we'll get started in another 4 to 5 minutes as soon as the clock ticks 7. Cool. Yeah, so no technical glitches and that's good to know. So let's wait for a few more minutes and we'll dive into the session itself. Again, I'm not fluent in Hindi. Somebody's asking me to say something in Hindi. I'm not fluent in it. So Hindi is not my mother tongue. So yeah, I'm much more comfortable in English. And I won't make mistakes, or I will make fewer mistakes, I should say. Cool. Again, for this session itself, I think we also made it clear in the announcement video. I hope all of you have seen the previous session, or at least know about multi-threading and multi-processing in general in Python, right? So I hope you know that because we'll build on top of it for the rest of this session, right? So cool. Can you expect a new course in data structures and algorithms in Python from Applied AI? So Vamsi, so our whole interview prep course has been done in such a way. Again, we initially did it with C programming in mind, but all of the code snippets, all of the code explanations, we've already added code in Python because students requested for it. So the interview prep course that we have covers whole of data structures and algorithms. So we cover all concepts from a pseudocode perspective. We explain code in C. We also explain code in Python, right? So we also provide code in other languages like Java in case you want to use that. But we try to explain concepts from a pseudocode perspective so that tomorrow, let's assume you want to use, let's say Go, okay? Or you want to use some other language like Scala. So you can use any language of your choice. That's what, to keep it generic, we try to use pseudocode. Again, we tried to follow the book, the CLRS book, Introduction to Algorithms in that. But on students' request, we have added code walkthroughs, we have added detailed explanations in Python also. So that you can already find there. Okay, cool. Shashwat. Okay, sorry, it was a tongue twister there. So how much time do you need to spend to complete Applied AI course in 1 year? From what we observe from our students, an average student needs to spend about 10 to 15 hours a week, right? So again, your learning will be slow in the initial 1 month or so, but slowly you will ramp it up, right? If you are putting in, again, we have some people who put in more time during the weekend, less time during the weekdays. That's perfectly all right. That's why we want to give you a number which is 10 to 15 hours. Again, depends on what, again, if you want to get into the best of best companies, it's better to put in 15 hours per week, which is roughly, which turns out to roughly 2 hours a week, roughly, right? 2 hours a day, 2 hours a day, roughly, and maybe a couple of hours extra over the weekend. So if you can put in that effort diligently without distractions day in and day out, it's fairly easy to complete the course in under 6 months, including the assignments. Okay, cool. So let's get started then. It's already 7 p.m. So I'll just change it to my screen. And the plan of action today is as follows. This is a 2-hour live session. There is a lot of stuff to cover and I don't want to take this to one more session. So what I'll try to do is I'll spend about 90 minutes or so, 90 to 100 minutes covering how parallel algorithms can be used for training, whether or for simple data science or machine learning or deep learning work, and how they can also be used for productionization. There will be few places where I'll do code walkthroughs, but a lot of the code walkthrough has been done in the previous session where we explained how to do multi-processing, how to do multi-threading, etc. Here it will be more about concepts. Okay, of course, there are some places where I'll do code walkthrough where I'll show you on my terminal how everything works. But let's try to cover more by understanding how parallel algorithms can be implemented. Again, this is a topic that I personally love a lot because I have worked on this specific problems extensively when I was working at different companies. And actually, again, this was pre-great libraries. So early in my career, I built many of these things from scratch, from the ground up. So I've had some really interesting experiences on building parallel algorithms, primarily for data science and machine learning applications. So we'll work on that. Okay, I'll discuss all of that in this session. Cool. Let's go into the session itself. Okay, so here is my notes. Okay, so I'll go through this whole notes. First, let's spend about 90 to 100 minutes going through everything. Then I'll open up the floor. I'll try to answer as many questions as I can. Okay, so yeah, the screen is being shared. Yes. Then I'll try to answer as many questions as I can. But please understand that it's almost impossible in a public live session to answer every question. So anything that I am not able to answer, feel free to email us at team@appliedaicourse.com. Either me or one of our mentors will try to respond to it as soon as possible. Okay, so let's get started today. So today's session is parallel programming for whether it's data science, machine learning or deep learning applications. And we'll focus a little bit on training and a little bit on productionization also. So I'll do more detailed code walkthrough for productionization. Again, we will do parallel programming based productionization using web APIs. So we have already done previous sessions where we talked about how to use Flask APIs in Python. Again, Flask is one of the very popular ways to build web APIs in Python. It's also used extensively in the industry, and we have already discussed that. So we'll build on top of Flask APIs and how to actually do parallel processing or parallel programming for productionization also. So we'll do some code walkthroughs, introduce a few new concepts here. For most of training, we will build on, again, in all of this, we'll actually take a few problems. So let me just show you that. Okay. We are a big fan of trying to solve problems and introduce concepts as we solve problems, right? So in the previous session last week, we learned about how to do multi-processing in Python and how to do multi-threading and what are the challenges of doing multi-threading in Python and why multi-processing is used extensively. We also discussed about libraries like joblib. We did a ton of code walkthroughs last week. So we'll build on top of these. In this session, we will design parallel algorithms for training machine learning models, whether it is in data science, whether it's in machine learning or deep learning. We'll try to cover a few examples in each of them. Then we'll spend some time discussing how you can use parallel processing for productionization of models, right? So just let me keep the chat window open on my phone. Just give me a second, folks. I want to keep it so that if there is any technical glitch, I will be able to see it in the chat window. Okay, cool. So yes, so this is where we are. Cool. Again, I'll come to the chat window. I'll answer your questions after we complete all the concepts that we want to discuss, all the code walkthrough that we want to do. So I'll try to allocate 20 to 30 minutes at the end just for Q&A. Cool. Okay. So now, most importantly, please realize that parallel processing is a very vast subject, right? You can spend weeks together learning about parallel processing. It's a non-trivially large subject. Okay, there are multiple books written on it. I have taken a parallel processing course as a graduate student. So it's a vast subject onto itself. Please think of this as an introductory session where we will not be able to go into a lot of details of parallel processing. We will think of this as an introductory session of parallel processing for machine learning applications. And the way we will learn these concepts is we will introduce ideas, we'll introduce new ideas as we solve a bunch of problems. Right? So as we try to solve a bunch of problems, we will introduce ideas. I think this is the best way because it will help you connect the concepts to theory better. Now, parallel processing itself is a vast area because there are many models of computation. Okay, this is also very important to make a note of because you could have a multi-core, multi-threaded CPUs. This is one computational architecture on which you can do parallel processing. And this is what we will focus on. Even in the previous session, we talked about hyper-threaded processors. We talked about, I showed you my computer which has 6 cores, right? My computer has 6 cores and it has hyper-threading because it's an i7 processor. So it can do hyper-threading. So there are 12 threads that we can parallelly work with, right? But parallel processing need not be, the general area of parallel processing, if you pick up any book or read about parallel processing, it's a very vast area, right? So you can think of computation on GPUs also as parallel processing. Again, we discuss about how GPUs are used for deep learning in our deep learning videos of our course, right? So that's also one way, that's also one architecture. There are also FPGAs, which are custom hardware that are built to compute, to do computations very fast. Okay, there is also clusters of computers. So we have done a few sessions on Spark, right? One of the sessions is also publicly available where we talk about how Spark works. So cluster computing or distributed computing is another computational model under which everything works. So there are many computational models in which you can perform parallel processing. We will stick, in this session, we will stick to a system where you have multi-core CPUs with multi-threads. Okay, we will not be able to go into GPUs or FPGAs or clusters in this. Or about distributed computing or cluster computing, we have discussed how Spark works, how Hadoop works, all of that earlier. Number one. GPUs, we have discussed about them in our course videos when we teach about how to use TensorFlow, Keras, and how GPU itself works, how GPU uses the thousands of cores that it has while using the video RAM. FPGAs is beyond the scope of this course because this is something that is fairly advanced. Okay, cool. Okay, sounds good. So just wanted to give you a heads up. Another very important question that many people have here is, what is the difference between parallel computing and distributed computing? So very often, again, these terms, I've seen people use them in many different ways. So there are many slightly variational definitions of both of them also. In general, when somebody says parallel programming, they're talking about multiple cores on a box. They're talking about multi-threaded systems, or they're talking about GPU-based systems. Notice that in all of them, the memory is shared by the multiple cores or the multiple threads or the thousands of cores that you have in a GPU. Okay, so all of this is happening in one box or literally one beefy computer where you have all the memory being shared. On the other hand, if you look at distributed computing, we have done live sessions on Spark and how to use Spark for machine learning. We have done I think 3 or 4 live sessions on Spark. Okay, we've also done live sessions explaining how Hadoop works internally, right? So we have done code walkthroughs of Spark and things like that. In all of these systems, what you have is a distributed memory, which means you have multiple computers here. Think of each of these as multiple computers. All these computers are connected via a network. It could be a very fast network. It could be like a 1 Gbps or a 10 Gbps or even a 100 Gbps network. But each of these computers has the RAM internally. So the data itself is distributed across in a distributed memory, which means the RAM is split. So there is RAM on this computer, RAM on this computer, RAM on this computer, RAM on this computer, etc. So suppose imagine if I have 6 cores here. Okay, suppose imagine if I have 6 cores on this computer 1, right? So this core can't access the data that is there in this computer's RAM, right? Of course, if it wants it, it has to fetch the data via the LAN, copy it to its RAM, and then access it. Okay, so distributed computing is typically used when you have large data. When you have large amounts of data, typically distributed systems like earlier people used to use Hadoop a lot, but nowadays most people use Spark for machine learning and data science applications, right? So we have already covered Spark in lots of detail in the course videos. Today we'll focus on, imagine you have one computer, or it could be a computer that you personally own, or it could be a cloud-based computer. If it has 6 cores, 12 cores, 30 cores, if it can support multi-threaded code, if it has GPUs. So we'll talk about parallel processing in this context. Okay, not in the distributed computing context. Just wanted to make that clear. Cool. So let's start with some simple problems. Okay. So imagine you want to add 2 matrices. Okay. Let's start with some very simple problems. Okay. Suppose you have 2 matrices A and B, and you want to add both of them and generate, let's say, C equals to A plus B. Let's assume this is what you want to achieve. Now, how do you do it? Standard matrix addition, you know how to write it, right? It's just a simple twin for loop. You go through each cell of A, you go through the corresponding cell of B, you add them and generate the set. So this is basically Cij equals to Aij plus Bij. So you write a loop for I and for j. I goes through all the rows, j goes through all the columns. It's just a twin for loop structure. Okay, this is how you write it in a standard computer. In parallel computer, Look at this, you have multiple cores, right? So again, a major assumption that I'll be making here is that both A and B fit into the RAM. Okay, I'm making this fundamental assumption that A and B fit into the RAM. Now imagine I have A, which is an n cross m matrix. B also has to be same sized, otherwise we will not be able to add them. B is, let's say, n cross m. Now you want to add both of them. Now again, so one simple way to do it. Again, there are many ways of doing this. One of the simplest ways you can do here is this. Take n1 rows. Take n1 rows of A. Take n1 rows of B. Add these n1 rows of A, add these n1 rows of B in one core. Let's say you do it in core 1. Suppose, let's say you have 6 cores on your computer. Okay, so look at this. Because you have to add this cell to this cell. This cell and this cell addition to produce the answer, you don't require other cells. Right? So you're taking this whole data. Look at this. You're taking this data. You're taking this, the first n1 rows. So the first n1 rows of A and B, you're going to send them to core 1. The next n2 rows of A and B, right? So next n2 rows, send them to core 2. So on and so forth. Okay, then what happens? Look at this. This is one simple way to create parallelism. Okay, now what is happening? While you are generating the first n1 rows of C in one core, another core is generating the next n2 cores of C. Right? So your final result is, let's say, C equals to A plus B. Let's assume that's what you want to generate. Right? The first n1 rows of C are being generated in the first core. This is happening in the second core. This is happening in the third core, and so on and so forth. Very simple mechanism. This is almost trivially parallelizable. Again, the technique that we are using here is called data parallelism. Why is it called data parallelism? The reason it's called data parallelism is because, look at this. Each core, if you have 6 cores, C1, C2, so on and so forth, C6, C1 is seeing a part of the data. You're taking the data, you're parallelizing the data. So C1 is seeing the first n1 rows of A and B, C2 is seeing the next n2 rows, and so on and so forth. Now by doing this, what are you doing? You're breaking the data, you're parallelizing the data here. So this is called data parallelism because each core is seeing a different subset of data. Right? And it's operating on a different subset of data. Now again, I hope all of you know what is a row major order. Okay, so depending on the programming language and the library you're using, lot of computers. Now you might say, okay, all this is cool. Why are we taking n1 rows and n1 rows here? Why can't I take columns? Why can't I take n1 columns here, n1 columns here, send them to core 1? Or n2 rows here, n2 columns here, n2 columns here, and send them to core 2. Now what happens is, in most programming languages, each matrix that you have is stored in row major order. What it means is, even though what you have, so what does a row major order mean? So imagine you have this row 1, okay, let me just change the color, row 2, let's say row 3, let's say row 4. Suppose you have these 4 rows. How is this actually stored in the memory? The way it is actually stored in the memory is as follows. First it stores row 1, right? Then it stores row 2, then sequentially it stores row 3, then it stores row 4. So even a matrix is stored actually internally as an array by most programming languages. Even a matrix is actually stored as an array. So this way of storing is called row major order, which means the first row is stored first, then the second row, then the third row, then the fourth row, and so on and so forth. In a column major order, first you store the first column, then the second column, third column, fourth column, etc. Most modern programming languages and most modern libraries use row major order. They use the row major order. So what happens now? Suppose if I want the first n1 rows, the first n1 rows will be consecutively stored in the memory. Right? Similarly, the first n2 rows will be consecutively stored in the memory. So accessing these rows is much easier because they are in row major, they're stored in row major form, right? So that's the core idea here, right? So this is a very simple thing. Matrix addition is one of the simplest of all applications. Now let's go and see slightly more complex example, right? So again, there is one more important thing here before we go into other examples. So what we have here is A plus B equals to C. Now we want to store A, B and C, all of them in the shared memory. Okay, look at this. Imagine this is your RAM, right? Imagine this is your RAM. You have A, B and C, right? You want all A, B, C to be accessible by all of your cores. So you have core 1, core 2, core 6. You want, look at this, you want this memory that is allocated to A, B, C. You want it to be accessible to C1 up to C6, all the cores and all the processes that are running here, right? Now, how do you do that? Okay, so there is a concept called as shared memory. Again, we discussed about it in the previous session, but let me show you a very simple code snippet. Again, this is from the official documentation of Python. I will share these notes with you at the end of this session so that you can go through this, right? So let me just let me just go here. Okay, so how do you create? Okay, so there is a very simple example here. Let me show you a simple example here. Okay, so I'll just walk you through. Let me just zoom this in a little. Okay, so this is a very simple example about shared memory. Okay, very simple code walkthrough. Let me walk you through it step by step. First, we are importing NumPy, right? We are creating a NumPy array. Okay, it could be anything. Remember, it could be a NumPy array, it could be anything. It could be a SciPy structure, it could be a data frame, it could be anything, doesn't matter, right? Next, look at this, from multiprocessing. Multiprocessing is a module that we learned about in the previous session, right? So from multiprocessing, we are importing something called a shared memory. Okay, we'll use this now. Now, we want to create a shared memory space. Okay, we want to create a memory space within the RAM. So look at this, within the RAM. So one very important thing here is if you have multiple processes, let's say you have process 1, process 2, let's say process 6. Let's say your process 1 is running in C1, process 2 is running in C2 and so on and so forth. Process 6 is running on core 6. Each process has its dedicated memory that all the code in this process can access. So each process has its dedicated memory. But now what we want to create here is we want to create some shared memory. So we are calling this shared memory, right? We want to create some shared memory that is accessible to all of these processes, right? And we will store A, B, C in this shared memory. Now, how do you create shared memory? It's actually very simple in Python. Okay. So you just say, so you create this variable called SHM. You say shared memory dot shared memory, create it. You want to create this shared memory and the size of this shared memory is A dot number of bytes. Because you want to place this, remember, you want this A to be placed in this memory. Okay, so this is already there. This is already in the memory. The moment you create this NumPy array, it's already in the memory. Now you want to copy its contents to a shared memory location. Okay, so you want, suppose this process is created A. Okay, so this process, let's assume, has created A. So A will be there in its memory. But now you want to copy this to your shared memory. So you're saying, I want to create a shared memory chunk, okay, whose name is SHM, whose size is A dot number of bytes. Simple. Okay. So now look at this. Now it says, now create a NumPy array backed by shared memory. Okay. So what are we doing here? Now we are saying B equals to NumPy.nd array. Okay. So we are creating a new array called B here. What is it? It's a NumPy array and its shape is same as the A dot shape. Its data type is same as the A dot data type. But the space that it should create, so what this buffer gives you in NumPy in mp.nd array is, this buffer equals to shm.buff. What this does is it tells NumPy that create an array, create a NumPy array called B. Its shape should be same as A, its data type should be same as A, but create it in this memory buffer or in this memory location that we have already allocated space for. So now what is happening here? Look at this. So what's happening here is this. Let me use a slightly different color. Okay. So let's assume A is stored here. Now as soon as this line runs, okay, so we've already added SHM. This is our SHM, which is our shared memory object, right? Now the moment you run this line, it says create another NumPy array called B with all the properties same as A, but created here. So this B will be created here. Since this is shared memory that can be accessed by multiple processes. Okay. Now what are we doing here? Look at this line. What does this line say? This line says copy everything from A to B. So if you print B now, you will get all the contents of A just as B. Now here comes the most interesting thing. So you can get the name of the shared memory. You can say shm.name. It will give you some alphanumeric string like this, right? Now using this alphanumeric string, you can access, see, you got a unique name, because SHM, remember, SHM is a variable name in this code snippet. Suppose this code snippet is running as part of process 1, right? Then SHM is actually a variable name. So SHM is a variable name in this process. So you can't access it using SHM. So you get some general name like this. You get a generic name which says, okay, what is the name of this shared memory as understood by Python? Next, you can start one more terminal. Look at this. You can start one more terminal, completely different terminal, or you can start one more process. In that other process, you can access the shared memory using this name, right? If you start a new terminal, right? Imagine you are using one terminal and you use another terminal. If you change the terminal, a new process is created effectively. So here also you just say, so in your child processes, you just have to say from multiprocessing import shared memory. Here comes the most interesting thing. You say shared memory dot shared memory. You give the name of the shared memory, and you give a variable name called existing SHM. Now what happens is interesting. Now this process, imagine this is process P1. This code is running in process P2. Now P2 can access. So where is our code? Okay. So let's assume this is P1 and this is P2. Right? Now process 2 can access whatever is here. Because we are using this unique name, right? We are using this unique name PSM underscore blah blah blah, right? Now, so we got this. Now we want to treat whatever is there in this memory, we want to treat it as a NumPy array, because what is it? It's just a bunch of bits and bytes. We don't want to treat it as a bunch of bits and bytes. We want to treat it as a NumPy array. So what do we do now? Very simple. Just create a NumPy array, give the size exactly as your A, give the data type exactly as your A. Okay, whatever is the size and data type, use it. Again, here A variable will not be there because A is a variable in process P1. You don't have A variable here. All you have to say here is buffer equals to, you have to give this name, existing SHM underscore buffer. So what happens now? Whatever is here, it will now be treated in this process as a NumPy array C. That's it. Now you can start modifying. See, if you modify C here, let's assume process 2 modifies something in C here, that modified value will be observed everywhere. Okay, so this is how you create shared memory which can be accessed across multiple processes. Okay, so that's all. Again, the reason I'm showing you code walkthrough from the official Python documentation is because if you want to read more, you can read up this whole article. Okay, it's again, the whole documentation is clear, all the function, again, this is from the most recent version of Python 3.8. So all the details are here. I want to walk you through actual official documentation so that if you want to read more, it will be easier. Okay, so I'll provide this link. I'll provide this whole doc for you. So all you have to do here is this A, B, C, let's assume they are NumPy and D arrays. You just have to place them in a shared memory. That's it. That's all you have to do. Okay, now let's go into matrix multiplication. Now you might say, hey, why are you doing all matrix operations? Let's go to machine learning models. Please understand that matrix operations are foundational to whole of data science, machine learning, deep learning. Look at any algorithms update rules, whether it's a machine learning algorithm like logistic regression, linear SVM, or deep learning algorithms. All of them are basically matrix operations, matrix multiplications, or you can think of them as matrix or vector or tensor operations, right? We'll come to vectors and tensors in a few minutes, right? They're basically multiplications and additions of matrices, vectors or tensors. That's what most of machine learning implementation is all about. If you, again, in our course, we have implementation of some of the algorithms, right, from scratch. Like we implement linear regression from scratch. And that's also one of the assignments that we have, right? So in all of those things, if you notice very carefully, this whole thing is a bunch of matrix, vector or tensor operations. And matrix multiplication itself is very, very fundamental to many, many scientific applications, not just machine learning and deep learning. Lot of physics simulations, right? Lot of physics simulations, lot of mathematical simulations. All of them involve ton of matrix operations and especially matrix multiplication. So there are many, many variations. There are tons of parallel matrix multiplication algorithms. We will not be able to cover all of them. There are actually full-fledged books which talk about just parallel matrix multiplication operations, like full-fledged books. Okay, so we will cover some simple ones. Okay, cool. So let's assume what we want is, okay, so let's assume what we want is matrix C, which is a product of A and B. So A matrix is n cross m, B matrix is m cross k. Okay, let's assume these are the two matrices that we have. And of course, C will be n cross k. This m and this m should match, otherwise it won't work. Very simple. Now, there are many algorithms. Let me introduce you to a couple of simple ones. Okay, the simplest one is as follows. Okay, so let me use a lighter color. Let's use data parallelism. So so on core 1, so always remember that on core 1, let's assume process 1 is running. On core 2, let's assume process 2 is running, and so on and so forth. Okay, we will multiply, look at this, we will multiply n1 rows here with all of these columns. What is matrix multiplication? You take a row, you take a column, multiply that, you'll get one entry in the matrix C. All right, that's what it works, right? So here also we'll apply data parallelism and we'll say the n1 rows of A. So let's assume process 1 will get n1 rows of A. It will get all of B. Look at this, it will get all of B, the whole B it will get. So it will read whole of B. But it will only use n1 rows of A. So then what happens? You can obtain, look at this row multiplied by this column. So first row multiplied by first column will give you C11. First row multiplied by second column will give you C12, right? Because C is the result, right? Then first row, third column will give you C13, so on and so forth. Similarly, second row, C21, you'll get C22, so on and so forth. So the first n1 rows of C, you can obtain by process 1, which is running on core 1. Right? Very simple. Similarly, the next n2 rows of A will be multiplied with the whole of B, in process 2. So this and this will be multiplied in process 2 in core 2, and so on and so forth. Right? So here also we are using data parallelism. Why are we using data parallelism? Look at this. B itself is commonly shared by P1, P2, all the processes. But only chunks of A are being shared. So one chunk goes to process 1, one chunk is used by process 2. So there is some amount of data parallelism here also. This is one of the simplest ways. There are many other different ways also. Okay. So another way, again, you can go and check this Wikipedia link, which says matrix multiplication algorithm. There are a bunch of parallel and distributed algorithms. One of the algorithms that is discussed on the Wikipedia page is as follows. So they say, imagine you want to construct C equals to A into B. Break A into 4 submatrices. This thing is a matrix. Remember, this thing is a submatrix. This is a submatrix. This is not one entry. This is not the cell A12. This is a submatrix A12. Again, another submatrix A21. So break A into 4 submatrices. Break B into 4 submatrices. Then you can write C as A11. Look at this, the first entry. Look at the first entry here. The first entry here is A11 multiplied by B11 plus A12 multiplied by B21. Of course, the sizes of these should match, otherwise multiplication will not be possible. Okay, so you multiply this submatrix, with this submatrix, whatever is the resultant that you get, you add it to this submatrix plus this submatrix. That will give you the first submatrix in C. Right? So this approach is a more generalized approach compared to here. Here, if you notice, whole B is fixed. We are breaking only A into subparts. Here, both A and B are chunked. Both A and B are broken down into submatrices, and you can write C as this. Again, this is fairly straightforward to see. If you know basic matrix multiplication, this is straightforward. So how is this done now? Look at this. This is slightly interesting, right? So first you have to multiply this with this. You have to multiply this with this, right? Then once you get all of them in the parent process, you perform this addition. First, you give all of your processes. In one process, this product will happen. In one process, this multiplication will happen. In one process, this multiplication will happen. In one process, this multiplication will happen. In one process, this will happen. In one process, this will happen. So each of these multiplications will be independently done by different processes. These multiplication values will be put in a shared memory location. Then in the parent process, we talked about parent and child processes, right? In the parent, so all of the child processes actually perform this matrix multiplication. In the parent process, we will perform the final addition. Okay, that's how you can do it. Again, if you want to learn about more algorithms, you can learn about it in this Wikipedia link. Okay, very simple logic here. Now, okay, so all this is cool. Again, there is a, okay, let me walk you through a small code snippet that is given here. Okay, so again, this is what I was referring to. Okay, so you can also see the code here. Okay, there is a very simple pseudocode written here, right? So here, remember that fork. So whenever you are reading this term fork is a term which is used in Unix or Linux computers. Fork basically means create a new process. This is equivalent to saying create a new process that we have seen in Python. We already talked about join, right? In the previous session, we talked about the join operation, right? So if you want to get a pseudocode of how to multiply by breaking A into 4 submatrices, right? B into 4 submatrices, this is one way of doing it. So it says first partition A, B, C, T is a temporary matrix. Then it says create one process to compute this, create another process to compute this, create another process to do it, as I explained you. Then join, which means wait for all of these jobs to complete. Once all of them are complete, just add things. Just add them. Because at the end of the day, what you need is this, right? So at the end of the day, you need to add this. This you will get it, this you will get it. You need to add both of them to get the final result. That addition is what is being done here. So what you see here is a simple pseudocode of what I just explained. Cool. So again, this is one way of doing matrix multiplication. Okay, so let me move on. Okay, another small topic that I want to touch upon because I want to tell you how, I mean, there is so much scope in parallel algorithms, right? So many of you may not know this whole architecture unless you have studied computer science. So I just wanted to give you. So whatever you have in hard disk, so data is permanently stored in hard disk or solid state drive, right? So it is loaded into RAM. So many people think that data from RAM is directly accessed by the CPU. So let's assume this is your CPU. Let's assume that your CPU also has 6 cores, core 1, core 2, so on and so forth, core 6, right? Now, if C1, C2 up to C6, all of them are 6 cores, between RAM and the cores, there are 2 more levels of memory. There is something called as cache memory, okay? And there is something called as registers. Registers are basically, there is, again, RAM can run into few GB nowadays, right? Few GB. This can run into few hundreds of GB, right? You have cache and you have registers. Registers typically are just a few bytes, okay? These are just few bytes. But registers are small memory units which are stored on each of the cores. So they're extremely fast to access. The reason cache is introduced is cache is almost 10 to 100 times faster to access than from RAM. Look at this. Accessing data from disk is very slow. This is very slow. Accessing data from disk is very slow. From RAM is fast. From cache is very fast. So from registers is very fast, right? So what happens here is, even if your data is in the RAM, again, your cache could typically run into few MBs of space. Again, modern microprocessors like your i7 processors, etc., have multiple levels of cache called L1 cache, L2 cache, L3 cache, etc. Now you might say, hey, why don't we have everything in cache? Because cache is expensive. They can't put 1 GB of cache. Cache is very expensive compared to RAM. So in a strategy to cut costs, they have multiple GB of RAM, they have few MB of cache and few bytes of registers, right? So now look at this. Now the most interesting thing, again, this is the standard architecture. Again, a lot of people don't know about cache. That's why I introduced this concept. Again, if you want to know more about cache, you have to study about how computer organization works, how operating systems work internally, right? But this much is enough for our context right now. Suppose imagine if our memory is in, if our ABC matrices are in RAM. If they were actually in cache, your code will run much faster because the cores can access cache 10 to 100 times faster if they were in cache than if they were in RAM. At the end of the day, they have to access this data, right? They have to access this data and perform an operation, right? So because the cache is becoming a very, very important part of modern microprocessors, there is a whole area of algorithms called as cache-aware algorithms, right? So there is matrix multiplication, which is cache-aware, which tries to ensure that we use the cache as optimally as possible so that we can speed up the whole multiplication significantly, right? So there is a lot of complexity. So if you really want to become an expert in parallel computing, you have to know a lot of computer architecture. So you have to know a lot of computer architecture, right? If you really want to pursue this topic in full depth. But for most data science and machine learning applications, you don't have to know a lot more depth, okay? Even if you can apply some basic stuff, that will speed up your workloads enormously, right? So, okay, cool. This is one aspect to it. Again, please understand that I see the comment section. Yes, there are many algorithms for matrix multiplication. There are recursive algorithms. There are distributed algorithms. There are a ton of them. Just in the interest of time, I'm only covering the basic systems because I'm giving you an intuition on how you can parallelize. Okay. This area, as I told you, there are full-fledged books on just parallel matrix multiplications, right? So hence we will not be able to go into it. So now the challenge here is you can't increase cache to a few GB because we are still not there. It's fairly expensive. Your computer will cost a few $1,000s if you just increase the cache like crazy, right? So there are pricing constraints. Most modern computers that you buy have RAM. They have some SSD, solid state drive or hard disk. They have a decent amount of cache. They have multiple cores and they have registers. So there are also cache-aware matrix multiplication algorithms that we will not be able to go into full depth. Again, those of you who want to learn more about it, about L1, L2, L3 cache, again, remember the way L1, L2, L3 cache works is as follows. L1 cache is the smallest, it is the fastest. It is closest to your CPU. Then you have L2 cache, then you have L3 cache, then you have RAM. So you can think of this as a hierarchy of RAM, wherein registers is also part of memory, right? Think of registers also as a type of memory. So as you come closer and closer to the CPU, the speed increases. Literally, as your memory is closer and closer to the CPU, the speed increases. The cost also increases, and the size reduces. Right? So basic logic, because you can't stuff 1 GB of RAM in each of the cores. You can't stuff them inside this, right? It's not possible today, right? So cool. So this is what you have. Okay. So just wanted to tell you about a whole area called cache-aware algorithms. I mean, it's a huge research area. Again, full-fledged books, tons of research papers written on it. Okay. Cool. So another question that some of you may have here is what we discussed about are matrix operations. What about vector operations? What is a vector? Vector is also an n cross 1 matrix, right? So whatever we have discussed for matrices also holds for vectors, right? Some of you may say, hey, in deep learning we use tensors. What about tensors? Imagine you have a three-dimensional tensor like this, n cross k. What is this? This is nothing but it's a bunch of k n cross m matrices. So all the logic that we have done, imagine you have a three-dimensional tensor like this. So imagine you have a three-dimensional tensor like this. You can chunk it in whichever way you want. So a matrix, look at this, a matrix we chunked it into rows, right? Here you can chunk it into cuboids. So this whole thing could be one chunk, right? So it all depends on how you chunk the data and how you design the parallel processing algorithm. But whatever we have learned for matrices can be scaled to tensors also, right? Imagine you have k n cross m matrices. Send each n cross m matrix to each of the processes if you can do the operation like that, right? So that's all it boils down to. Okay, whether you have vectors, matrices, tensors, the basic concepts that we learned here are applicable everywhere. Okay, again, please understand that we will not be able to go and spend a lot of time on lots of internals of all of them. I'm just trying to give you an idea on how, again, this is primarily for data science and machine learning folks, right? Okay, now let's get into machine learning training. Okay, again, here I'll talk about some of the concepts and we will keep going into these. See, whether you have logistic regression, whether you have linear regression or linear SVM, at the end of the day, how do you write code? When you have to implement this from scratch, how do you do it? You have, let's assume you have a weight vector W. which belongs to d dimensions, which belongs to Rd, which means it's a d-dimensional vector. Now, at each iteration, okay, whether you're using gradient descent or stochastic gradient descent or batch SGD, whatever you're doing, you're basically updating W new. See, Wi is nothing but the ith component of W. So I'm writing Wi as the ith component of W. So in each iteration, what do? Wi new equals to Wi old minus some learning rate multiplied by the derivative of the loss function with respect to Wi as computed at Wi old. Basic logic. Again, this derivative itself will change from linear regression to logistic regression to SVMs. Again, this loss depends on the exact loss function that you are using plus regularization. When I say loss here, what I mean here is the loss function. You could use a logistic loss plus regularizer. Logistic loss is nothing but cross entropy loss. Linear regression, you can use squared loss plus whatever regularization you want. If it is SVM, if it's, let's say, linear SVM. If it's a linear SVM, what do you have? You have hinge loss plus L2 regularization, right? So this L basically is loss function plus whatever regularization you have. So whatever I'm discussing here is applicable to logistic regression, linear SVM, all of them. Okay. Now, one of the most important things here is this part. Look at this chunk. How do you compute this? This loss typically has some summation over all the points. Okay. Whether you have again, depends on how you are implementing, right? So you could have a loss over all the points. So let me use J here just to avoid confusion with I here. Okay. So this loss itself, this derivative of the loss again, this derivative will change whether you're using logistic regression, linear regression or linear SVM. This itself could be a summation over all points, right? Or it could be a summation over some K points if you're using a batch size of K, right? Typically. So this typically involves a summation over J. Typically involves a summation over J. This J itself could be 1 to N if you have N training points, or it could be 1 to K if you're using a batch SGD. That's what it is at its very core. Again, we explain the mathematics behind this in lots of detail in the course videos. We've also explained it in some of the live sessions. Okay. So we will, because from an implementation standpoint, this equation is what you have to implement at the end of the day. Now, there are many ways of implementing logistic and linear regression. One of the ways is, let's do task parallelization. So what we saw till now is data parallelization. So let's look at task parallelization. So what we'll do is this. Our W, let's assume, is a d-dimensional vector. Okay. So this update equation needs to be executed for each of the Wi's. So from W1, W2 to WD, because W is a d-dimensional vector. This update equation needs to be executed for each of the Wi's. Okay. Now, one of the simplest ways, I'm not saying this is the only way, this is one of the simplest ways, is you can say some of these Wi's you will update on core 1. A bunch of these Wi's you will update on core 2. A bunch of them you will update on core 6. Again, on core 1 you have process 1 that is executing, on core 2 you have process 2 that's executing, on core 6 you have process 6 that's executing. Now, one thing that you have to understand here is, the training data is used by all these processes, because to update any Wi, because if you notice, to update any Wi, you need whole of the training data, right? If you are using simple gradient descent, you need whole of the training data, right? Or even if you are doing SGD, you need a sample of this data, right? So effectively, what the solution that you want is, so the way you're distributing here is, remember that W1, updating W1 is, once you update W1, look at this, once you update, so you can, okay, the way it will work is, let's assume you are in iteration 0, okay, suppose you have W0 which is initialized, then you did W1. The subscript here tells the iteration number, the superscript tells the component number, okay, then you have W2, so on and so forth, okay. So first W0 is initialized randomly, okay, that you can easily do, okay. W1, some components of W1 are updated in process 1, some components are updated in process 2, and so on and so forth. Once all of them are completed, then you go to the next iteration and then you update them and so on and so forth, Okay, so the way you can tackle this problem, you can do task parallelization here, because what is your task? Your total task is to update from W1, W2, so on and so forth up to WD. So you have to update all of them. You have to run the update equation for all of them. You're breaking this big task into smaller tasks. Some of them you'll do it in process 1, some of them you'll do it in process 2, some of them in process 6, whatever it is, right? Now here remember that the whole training data needs to be accessible to each of these processes, and the whole weight vector is also being updated. So you'll have your D train and W in your shared memory. So the way you can, again here we are using task parallelism, because the whole of D train is accessible. The whole training data and the W vector are accessible by all the processes and all the cores. We are breaking the larger task into smaller tasks. So this is the idea of task parallelism. Now here one thing that you have to be very careful here is, imagine you are in iteration 0, wherein you have randomly initialized W's. Okay, random initialize. Now W1, after first iteration you are updating this. So here when you want to update the first iteration, you call each process and you tell each process that process 1, please go ahead, update these dimensions. Process 2, please go ahead, call the process 2, ask it to update these dimensions. Process 3, so on and so forth. Now when all of them are completed, then go for the next iteration. Okay, then go for next iteration and so on and so forth till the time you have convergence. Okay, this is one way. I'm not saying this is the only way of doing it. This is one of the simple ways of parallelizing linear or logistic regression. Okay, or any machine learning model where the update equation looks like this. Okay, cool. Now obvious question here is, what if D train doesn't fit into RAM? What do you do then? Right? It's a good question, right? What if your whole training data doesn't fit into RAM? Obviously, there are only a bunch of solutions. If you still have only one computer, what do? You break your whole D train into chunks, D1, D2, D3, D4. You load D1 into your RAM. And build your, again, here you can use all the 6 cores. Update your W vector across these 6 cores. Once that is done, then use D2, then use D3 and so on and so forth. This is one way. If you are to stick to only one, if you have to stick to using only one computer with multiple cores. But if D train doesn't fit into RAM, if it's so large, then you might want to use distributed computing like Spark. So in our Spark videos, we explain how logistic regression is trained on Spark using Spark internals, using map and reduce commands, right? So we talk about reduce by key, how map works, how distributed memory works in Spark, all of that, right? So a better approach, if D train doesn't fit into your RAM, or if D train, let's assume D train is, suppose your RAM is 4 GB, okay, and this is, let's say, 1 TB of data. Of course, you can use, suppose if you have only one computer, you can still use this method. It will take more time. But if you want to do this fast, then you can just go to Spark, spin off a cluster with some 20 or 30 nodes, Spark nodes, and you can use distributed computing there. Okay, so that's one of the approaches. Cool. So what about, so I just want to touch upon some more techniques here, and then I'll go into the Q&A session. Okay, I'm just looking at the comments to see what people are asking. I'll try to answer them at the end of it because I don't want to lose the flow. Okay, I'll surely answer as many questions as I can. Cool. So next is decision trees. Okay, how do you train a decision tree? Very decent question, right? There are multiple strategies with decision trees also. Again, I'll not be able to touch upon every machine learning algorithm, but since decision trees are uniquely different from the optimization based techniques of logistic, linear and linear regression and things like that, I want to touch upon this. Suppose imagine you're training a decision tree here. Okay, so there is some decision tree above. You are at some node. Okay, you are at some node. The data at this node is D1, let's say. Now at this node, let's assume you have D features, feature 1, feature 2, feature 3 up to feature D. Now you have to decide on which feature you want to split so as to have maximum entropy gain, right? So let's assume you're trying to, this standard decision tree building, right? So you want, so at this node, you have D features that you have to pick from. Each feature, some features could be categorical, some features could be real valued, it could be anything, right? Some features could be numeric, but like integer valued, whatever it is, doesn't matter. Suppose if you have D features and you want to decide what feature should you split here with, okay, what do you do there? Now here, one strategy is to use task parallelism. Okay, what does the task parallelism say? Task parallelism says, here we have to try feature 1, find the best split for feature 1. Okay, so how does this work? I mean, what is a brute force way of doing it? So if you were to implement a decision tree from scratch, first you will try feature 1, try to find the best split for feature 1, which gives you best entropy gain. Then you will try for feature 2. Feature 2, let's find the best split and whichever split gives you the best entropy gain, and so on and so forth. Okay, you try all the D features, and whichever feature gives you the best entropy gain, you will split this node based on that, and it will create two data sets. Okay, so this will go ahead and create D11 and D12. Again, you'll start training, you'll start split. So let's assume it creates two nodes. Again, data also will be split here, and then you will construct this subtree and you will construct this subtree. That's how decision tree works, right? Here we can use one strategy is to use task parallelism, wherein you'll say, okay, some features send them to core 1. Okay, these features, the best split and the best entropy gain for these features will be discovered on core 1. For another set of features, they'll be found out on core 2. Another set of features on core 6, and so on and so forth. So what are we doing here? We are doing task parallelism here. Because anyway, what is our task here? Our task here is check out each of these features, find the best split which gives us best entropy gain per feature, and then amongst all of them, pick the best. Pick the best amongst all of them. So amongst these, first pick the best. Imagine in core 1, you realize that, okay, feature 2, for some threshold, let's say some threshold tau 2 has the best entropy gain. So here you realize that feature 10, where the threshold is tau 10, right, has the best entropy gain, and so on and so forth. Now amongst all of them, you will have to find whichever has the best entropy gain and use that here. Now remember that each of these cores or the processes that are running on this course need access to the whole data D1. Right? They need whole access to the data D1. Otherwise, they will not be able to compute the best split and the best entropy gain threshold for each feature, right? So what happens here is the best split and entropy gain per feature is being split across cores, right? So very simple. Again, this is one strategy. I'm not saying this is the only strategy. Another strategy is as follows. Imagine you're building a decision tree here. This is your original data D. Okay. So on one computer, you discovered that, okay, so on one process, you can say, okay, some feature 2 less than tau 2. Okay. Yes, no. Okay. So what happens now? So the moment you have a data set D here and you have, let's say, some rule like this whole data D will get broken into two data sets, D1 and D2. Now this whole subtree, now remember, this whole subtree will be built using D1. This whole subtree will be built using D2. And the construction of this subtree is independent of the construction of this subtree. So this whole subtree can be constructed on some cores. Let's say on core 1 and core 2 we can use for this subtree. We can use core 3 and core 4 for this subtree. So here what are we doing here? We are using data parallelism. Because what is seen, look at this, because the whole data D now, the whole data D is split into data sets D1 and D2. So core 1 and core 2 now, where process 1 and process 2 are running, they only look at data 1, they don't look at D2, right? Well, C3 and C4 will only look at D2. This is another form of parallelizing decision trees, right? So there are broadly two broad approaches. Again, there are many other approaches. There are at least 20 research papers that I have read on decision tree parallelization because I implemented some of this in practice. Now, most people don't end up using decision trees in practice. What they end up using is random forests or GBDTs, right? Much more sensible models, right? So how do you train a random forest? Random forest is often referred to as a trivially parallelizable model. So all you have to do is this. Imagine you have 6 cores and you have to train, let's say, some 100 base learners. Suppose you want to train 100 base learners in a random forest model. Trivial, okay? So train tree 1, okay? T1 will be trained on C1, T2 will be trained on C2, T3 will be trained on C3. Again, the training of each of these is independent. Okay, T1's training doesn't impact T2's training because you do sampling, right? You do sampling and then you construct your trees. right? Row sampling, column sampling, all the ideas that we discussed in the course videos. So what happens? Suppose if you have 6 cores, T1 to T6 can be parallelly built. Once you finish constructing T1 to T6, then you can construct T7 to T12. Keep doing it, so on and so forth. So it is trivially parallelizable algorithm, right? So here one more idea from a programmatic standpoint that I want to talk about is this. There is a concept called as pool of processes. I just want to talk to you about it, okay? Because it's a very useful idea when you have a system like this, okay? Suppose, imagine there is a possibility. So the pool of processes concept is this. So first you create a pool, okay? Suppose you create P1, P2, P3, let's assume P6. Suppose you create 6 processes, okay? On this process, suppose you are creating some tree 1. On this process, tree 2, so on and so forth, T6. Now, after you create these trees, you want to again call the same process. So you have a pool of processes here. Think of them as pool, and each process is running on one core. You can reuse these. Imagine if you want to reuse these processes, you want to call these processes are running in the background. Okay. After you finish T1 to T6, you don't want to again spin off 6 more processes. Reuse just the processes that we have already created, right? And make something run on them, right? Because creating a new process is time taking. So process creation takes time, right? Process creation takes time. So in this pool of process concept, what happens here is, first at the very outset, you create a bunch of process. P1 which is running on C1. Let's say this is running on P3 running on C3. Suppose you create a bunch of 6 processes. You can call whatever function you want in these processes, right? Run, it will give you an output, again give one more input, it will give one more output, and so on and so forth, right? So that you don't have to keep creating the process, because process creation is wasteful, because it takes time. So there is very nice documentation on pool of workers. This is also called as a pool of workers, okay? Again, we'll use this concept of process pool in productionization also, okay? So some simple examples here. Again, I'll share the document with you, you'll be able to see it. I'm walking you through examples in the official documentation of Python itself. So actually it's very simple, okay? There are multiple examples here. Actually, let me show you a more detailed example instead of a simpler example. This is an example that I like, yes. Okay, so this is a slightly lengthy example, but it shows lots of cases. So all you have to do here is this: from multiprocessing, import pool, right? Simple stuff. Suppose you have a function f of x which basically squares the function, okay? Next, this is my main function. In this I'm saying this is a loop that I'm running. Sorry, this is not a loop, sorry, this is not while, I'm sorry. So first I'm creating a variable called pool. Look at this, what am I doing? I'm saying pool equals to pool. So this lowercase pool is a variable name. The uppercase pool is basically my class name, okay? Pool, and I'm calling the class constructor, and I'm saying processes equals to 4. The moment I run this, what happens is this: it will create a pool of 4 processes, P1, P2, P3, P4. It's creating these processes. Once it will create these 4 processes, each process will run on some core. This could run on core 1, this could run on core 2, this could run on core 6, this could run on, let's say, core 5. Okay, they could run on different cores. The moment I have these processes, I can start running something on the processes. Let's look at a simple example here. What this does, look at this function. It says pool.map. Okay, what we want to do here is we want to run this function f. So we want to run this function f, and the parameters that we want to give are range 10, which means we want to run f0, f1, so on and so forth up to f9. This is what we want to run. And what does it say? It says pool.map, which means the pool of processes that I have from in these pool of processes, please run f with f0. So probably f0 will go to one process, then f1 will go to another process, then f2 will go to another process, f3 will go to another process. Once these processes have completed and returned the values for f0, f1, f2, f3, then f4 will go, then f5, f6. So here you have 10 function calls which are being split across these 4 pool of processes. Okay, so if you want to compute something, if you want to compute f of I and you have this I here, this is one way you can split it across the 4 pool of processes that you have. So this is one way of doing it, right? Very simple logic. Now, number 1. Number 2 here is you can also say, okay, so this is the standard way of doing it, or you can say pool dot IMAP unordered. So what this does, so this basically sends F0 to the first process, then F1, F2. So this will actually print 0 square, 1 square, 2 square up to 9 square in the order. What this will do here is it will send it in arbitrary order. So when you actually run this, you can get 0 followed by 4 followed by 1 followed by 16 followed by 9, any order you can get it, right? So IMAP unordered basically means whatever are the values that you have here. So range 10 has 0, 1, 2 up to 9, right? So they need not be executed in any specific order. They could be ordered. I mean, first I could run F0, then I could run F2, then I could run F3 in any order. Doesn't matter. Okay. So this is how you can use a pool of processes again. There is another very nice syntax, which is, suppose you have a pool of processes. Let's assume you have P1, P2, P3 and P4. Suppose you only want to run, let's say F20. There is only one that you want to run, but you want to reuse these 4 processes that you have that are running on a bunch of cores, that are running on 4 cores. Then what can you do? You can actually say pool.apply async. So apply async basically means just call F20 on any of the processes that you have asynchronously. Don't worry about it. I just want to run F20 on one of the processes that you have. So all you have to say here is apply async F and the parameter is 20. That's it. So this will return a result. So you can get the result by saying result.get. Res.get, it will say, it will print 400 for you. So you can run these processes, you can run just one function call also in one of these processes. Or you can just give an array and it will run there. That's another way. Similarly, if you can do many more complex things. For example, look at this. Look at this function. So here, if you notice, we imported OS here. So all the operating system functionality, we'll get it, because this module gives us operating system functionality. Look at what is being run here. Look at this code here. What this code does is it says pool.applied async, okay, which means this whatever function you have here will be run on one of the processes. What is the function that we are asking? os.getPID. PID means process ID. So in any Linux system or any Unix based system, PID means process ID. So what would it do? It would run os.pid function without any parameters. It would run it on one of the processes. So what will you get? You'll get the PID of one process. It runs only in one process. That's important, right? That's one way. Or if you want to run it on all the processes, you can again run apply async and you can say for I in range 4. All right. So then it will run on different systems. So all these are, again, mostly you will use pool.map in most real applications, or pool.imap or pool.apply async. So what this gives you is, it gives you a pool of processes that you can keep reusing. So in the case of random forest, you can say, okay, so you could have a function. You could have a function that's implemented which says train the forest. Okay, sorry, train a base learner. All the parameters to train the base learner, you can just pass it. So probably, suppose if you have 6 processes, process 1 will first run this, process 2, process 3, process 6, again process 1 will run this, process 2 will run this, process 3 will run this, and so on and so forth. So pool of processes is very useful when you have to train a random forest. Again, we'll see how this is useful when we productionize models little later. The next very interesting thing, how do you do it for gradient boosted machines or gradient boosted decision trees? How do you do it now? Now, again, this is the update equation for gradient boosted decision trees, right? For those of you, again, I've taken this from Wikipedia. We also explain this in loads of detail in the course videos. So what it does is, this is the model after you build M base learners. So the model after M base learners is the model after M-1 base learners plus a multiplicative term called gamma M, which we discover by solving a simple optimization problem, multiplied with the mth base learner. Right? This is the formulation of GBDT, right? If you have to train a GBDT model from scratch, you keep finding each base learner, right? Again, to train base learner, you need to get the residuals from the previous from the previous models. So to train HM, you need residuals from Fm-1x. So what it happens is, first you build your, initially you have your H0x, which is your 0th base learner. Then you have your first base learner. To construct the first base learner, you need the residuals from the 0th base learner. Then you construct H2x. To construct H2x, you need the residuals from the residuals based on these two models, and so on and so forth. So if you think about it, to construct any HMX, to construct any base learner HMX, you need all the previous H0 to Hm-1x to be already constructed. So it is inherently serial. You can't parallelize this. You can't construct H01 in one box, H1x in another box, H2x in another, in one core, this in another core, this in another core. You can't do that. Because to construct HMX, you need all the previous models and you need everything up to Hm-1x, and you need the residuals of Fm-1x, right? So it is inherently serial, but still GBDT can also be parallelized. Very simple. So each base learner, remember in GBDT, each base learner is a shallow base learner, typically 2 levels deep or so. So each base learner, why don't you construct each base learner? Again, base learners in GBDT is a decision tree. So we have discussed how to parallelize decision tree construction just a few minutes back, right? So for GBDT, you can say this is your HMX. So parallelize the construction of each base learner, but you can't parallelize this part, okay? Because this equation or coming up with HMX, you have to have all the H0x up to Hm-1x. You need all of that. So you construct one after the other, but the construction of each base learner, which is basically a decision tree, you can do that. You can construct this decision tree parallelly, either using task parallelization or using data parallelization that we just discussed. The reason I discussed about decision tree parallelization is because both task parallelization and data parallelization mechanisms are actually used in GBDT. If you look at the source code of XGBoost or any of the major boosting methods, that boosting code bases that you see, they all use these. They all use these methods. They use either data parallelism or task parallelism or a combination of both, right? So, okay, cool. So now what about deep learning models? Okay. So again, remember that. Okay, let me show you a simple example of a deep learning model, right? So imagine you have a bunch of layers here. You have a layer here with 5 activation functions. Then you have a layer here with 3 activation functions, and then something else after this. So you have a weight vector here, weight matrix here, which is W5 cross 3. Let's assume it's a multi-layered perceptron, right? If it's a multi-layered perceptron, you have W5 cross 3, right? Again, you could have a CNN. If you have a CNN, what do you have? You have basically convolutional kernels here, right? Whatever it is, at the end of the day, you have some sort of matrix operation here. So in forward pass, look at this. First you have to do, see, how do deep learning algorithms work? You have a forward pass, then you have a backward pass. Very simple, right? Forward pass is nothing but matrix multiplication followed by some activation function that you apply, right? At the end of the day, that's what it is, right? That's why when Google wrote their code, they called it TensorFlow. Why did they call it TensorFlow? Because what it's doing is basically a bunch of tensor operations, and the flow here is basically the graph-based flow, the computational graph-based flow, okay? So at the end of the day, most deep learning is basically matrix and tensor and vector operations, right? So if it's a simple MLP, your W5 cross 3, which it's nothing but so you have outputs from here, you multiply them with this, and then you apply an activation function. That's what it is, right? So it all boils down to matrix multiplication. Your forward pass is basically matrix multiplication along with some activation functions, right? That's all it is. So we already discussed how matrix multiplication can be parallelized. So all forward pass can be trivially parallelized. Now what about backward pass? Look at this. When the errors or the partial derivatives, okay, the backpropagation is nothing but its chain rule with memoization, as we discussed in our course videos, right? So you get some partial derivatives. Based on those partial derivatives, you have to update these weights, right? Again, this is also trivially parallelizable. You get your partial derivatives in your backpropagation. Suppose this is your W5 cross 3 matrix that you want to update, okay? Simple. On core 1, update some of these weights. On core 2, update some of these weights. On core 3, update another set of weights. On core 4, update another set of weights, right? So again, look at this. Each of these, your Wij in kth iteration needs to be updated using an update rule, right? So let's assume each of this is W11, W12, so on and so forth. In the kth iteration, imagine all of them has to be updated. Some of them you update in core 1 based on the partial derivatives you get. Again, your partial derivatives are nothing but function calculations that you do. right? You can implement those partial derivatives in just a simple function. Your dou L by any weight, right? Dou L by any weight that you have is just an actual function, depending on the activation function, depending on the previous operations, right? So your forward prop is basically simple matrix multiplication. Your backward pass, you can trivially parallelize by updating some of these weights here. Okay, some weights on core 1, some weights on core 2, some weights on core 3, some weights on core 4. But for deep learning, typically GPU based systems are much faster. Again, we discuss this in lots of detail when we discuss about GPU architecture in the course videos, and the idea is simple. GPUs typically have hundreds or even thousands of cores. Okay, GPUs typically have thousands of cores. These cores are not very powerful, but because you have thousands of cores, all of these weights can be parallelly. Suppose imagine you have 1000 weights here. Okay, you have 1000 weight vectors here. All of them can be updated in a single shot here, right? When you have thousands of cores. So GPUs are preferable than multi-core applications for most deep learning, but you can also train it on multi-core systems. I'm not saying you can't train it. That's the key idea. Now, the same logic applies. See, most of deep learning, whether it is CNNs, whether it is transformers, right? Any model that you have, whether it is LSTMs, anything that you have, all of them boil down to simple matrix multiplication and updating your weights or parameters for every layer. So whenever you have a bunch of weights or parameters, whether it's convolutional kernels, whether it is whatever weights you have, right? The weights or parameters of an LSTM unit or a transformer encoder layer, whatever you have, all the weights that you have in a single layer, you can update them parallelly, because each of the weights, the core reason here is very simple. Look at this. These weights are independent of these weights. So you can update them in one core, you can update these in another core. Right? Similarly, whether you're using a transformer model or you're using any model, all the weights in any single layer that are independent. Suppose you have some weights, you have a weight matrix in one layer, right? So you can chunk some of these weights, you can process them on core 1, some of them on core 2, so on and so forth. So wherever there is independence, wherever there is no dependence amongst these weights, try to parallelly process them. And this holds true for most deep learning models. Now, I'll try to spend some 15-20 minutes on productionization, then I'll spend time on Q&A. Okay, so let's go to productionization first. This is also an important topic. So first and foremost, we discussed about, so we have done multiple sessions on how to build Flask APIs. So a Flask API is a web API. This is one of the very popular. Flask is also very lightweight, very easy to build. We have done tons of sessions on how to build web APIs for productionization of models. What do? You give an X as an input here. This computes your model. Let's assume your model is f of X. So you give X as an input. The Flask API, you can call this using web-based systems. You can give the IP address, port, right? So we discussed about some of these when we explained how to design Flask APIs and build them from scratch in the course videos and previous live sessions. So you give X as an input, it computes some function, gives you output. That's what it is, right? At the end of the day, this function, you can implement it in your code. This function could be, suppose you have logistic regression model, right? So you give X vector as an input, the fx computes the yi. So let's assume this is X, it computes the y, the class label, it outputs that. Okay, very simple system. Now things become slightly tricky. Imagine you have multiple people who are simultaneously requesting. So this guy is, let's say, sending x1, this guy is sending x2, this guy is sending x3, so on and so forth. Now you might say, where does this happen? Imagine our Flask API is doing a recommendation system. Let's just say, I'm just trying to give an example. So this Flask API, every user sends some data related to the user, then it has to return a bunch of similar movies or similar products. Okay. So let's assume you have an e-commerce website. What happens here? One user will have some properties. So all of his properties, let's say, are in x1. He'll give x1, we have to give y1 back to him. Now, it's not always necessary that only one person is accessing our website, right? There will be thousands of people who are simultaneously requesting this system. Now, this Flask API, remember, this Flask API takes this request and gives the output. Now, can you run this function f of x on multiple cores of your computer? So imagine you have core 1, core 2 up to core 6, right? Can you run this f of x? So let's assume this x1, this person sends x1. So can you compute f of x1 on this core and give y1 back? This person sends x2. So while f of x1 is being computed here, can you accept this request and also process it on another core, because you have multiple cores, right? So this is where parallelism in productionization is used. So here there are many solutions to this problem. One simple solution that is actually recommended by Flask itself for productionization is, they say, use something called as a WSGI. Again, this diagram has been taken from dzone.com. Very interesting repository of nice articles. So WSGI basically stands for Web Server Gateway Interface. So what it does here is, so each of your users is a client. Each of your users is a client, right, who could be accessing our website from, or who could be accessing our API, right, from a web page or from some program or whatever it is. First, they request something. Okay, they send us a request. They say, hey, here is my x1, please give me y1. This application executes our f of xi. Let's just say this application code. This application code is where our f of xi lies. So a WSGI, you can think of a WSGI as sort of like a web server like system. What it takes is, if multiple people are giving multiple requests, it will call the application in a very ingenious way. Okay, so it will take care of all of that for you. It will take care of the parallelism for us. So whenever multiple requests are coming in, it will call the application and it will say, hey, evaluate this. Once you have the response, send it back. I will send the response back. Okay, so WSGI is basically a piece of software. It's a web server gateway interface which enables us to be able to handle these requests in a server-like setup. Again, WSGIs are typically fairly lightweight. These are very often used with Flask. So one of the popular WSGIs is called Gunicon. Okay, it's actually green unicorn. So again, you can see all the documentation of Gunicon here. I'll show you some simple code snippets for it. It's a very lightweight, very simple system. So if you go to the Flask productionization on its official documentation, you'll see Gunicon as one of the WSGIs that it uses. So what does Gunicon or green unicorn? It's basically a WSGI HTTP server which is designed primarily for Unix based systems. Remember, a vast majority of production systems are Linux or Unix or equivalent systems, right? So Gunicon is very extensively used with it's extensively used with your Flask APIs. So what Gunicon does, look at this. So you have G Unicorn. So let me just show you how it works actually. Then I'll show you the code. Okay. So how Gunicon works is this. This guy sends x1, this guy sends x2, this guy sends x3, and so on and so forth. So Gunicon, what it does here is, it has a pool of processes. So it knows that I'll have to run this function fx. It knows that. So first what it will do is, it will create a bunch of processes, P1, P2, so on and so forth. Let's say P6. Okay, it creates a bunch of processes. Whenever somebody requests, it sees which process is not currently processing anything. So then, because it knows what function to execute. It knows about this whole Flask API, what function to use, all of that. So Gunicon now takes care of parallelization and orchestrating and parallelly distributing. So it sends x1 to p1, x3 to p2, and so on and so forth. It tackles all of that for you. And if all the processes are busy, Gunicon will internally store these requests in a queue-like system such that as soon as the processor freed up, it will coordinate all of this for you instead of you having to write the code. You can write this code yourself, but why bother about it? There's a very nice, good open source code that lets you do that, right? So that's one way of doing it, right? So as far as the code itself is concerned, I've just pasted the whole code here. Again, this is on a Linux or a Mac system. On Windows, some of these commands might change slightly. So you can install Gunicon. Again, if you want to read more about Gunicon, you can just go to their website. It's a very simple website, very easy to read. But let me walk you through the code snippet here. Okay, first, you pip install Gunicon. Very simple. You don't have the very simple implementation. So first, I have written something called myapp.python. Okay, again, all of these examples have been taken from the Flask official documentation and Gunicon website itself. Okay, so imagine I have my app, some application that I'm writing. So let's assume the application code is this. Okay, what are we doing here? We are importing Flask. We have a Flask app that we created, and we are saying if this is called, I have a very simple function called hello world, nothing fancy. I have a very simple function called hello world, nothing more. it just returns hello world. This function could be anything. Our f of x, we could just implement it here. And how to implement Flask with parameters, all of that, we have discussed that in other videos where we spent almost 4 hours on explaining Flask internals and how to design Flask APIs from scratch. So I'll not be going into the depths of Flask, okay? But simply speaking, this is a function that I would like to call. Here I'm just importing and creating a basic Flask app. Here I'm saying, if you just run this, just run the Flask app. Cool. Now, if you run this Flask app, let me just run it on my terminal so that you can see it actually running. Okay, 1 second. Sorry, I was running something else. So just let me show you this. Okay, so what was I telling you? Okay, so it's called my app, right? So what is my present working directory? Okay. Okay, so I have myapp.py. Okay, so if I just run myapp.py, sorry, Python. Okay. Okay, if I just run this, look at what it says. It says the Flask app, my app is running. Okay, but it gives you a warning. It says this is a development server. Do not use it in productionization systems. Use a production WSGI server instead. This is the official Flask statement. Look at this, what it says. This is very, very important. Flask itself says what you're doing is okay when you're trying to develop systems. But if you want to productionize this, please use a WSGI server instead. Gunicon is one that we are using. Now, if I just go to HTTP 127 this on my web browser, so I'm just running my Flask app right now. Nothing more fancy than that. Okay. If I just go here and run it, it will just say hello world. Okay. Very simple system. Nothing. I mean, I'm just calling a Flask API. But this Flask API is only using one core, right? It's not using multiple cores of my computer. So if I want to use multiple cores of my computer, the best way is to use the WSGI, which is Gunicon in our case. Okay, so the way we'll do it is this. We will create a simple code snippet called wsgi.python. Okay, in the same folder. So let me show you that just quickly, so that you will be able to. Let me show you the. Okay, look at this. myapp.py is in the same folder as wsgi.py. Okay, so if you go to wsgi.py, all I'm saying here is from my app import app. Remember, my app is there in the same folder, so I'll be able to import app. Whenever I run this function, just run app.run. And what is this app? Look at what is this app now. This app is nothing but this app, right? My Flask app that I have here is what will run. Okay, I've just created a different small code snippet called WSGI. Okay, so if you see the source code of WSGI, all that I'm saying here is this. So whatever I'm running in WSGI, whenever wsgi.python is run, just run app, just execute this app. That's all I'm saying. Now the Gunicon command that I can give here is, I can say Gunicon -w4. This means create 4 worker processes. Remember, this whole Gunicon itself is going to run on one process. Let's call it the parent process. Okay, so the whole Gunicon itself will run in one process, right? It has to run on some core. It will create 4 worker processes or 4 child processes. Let's call them as P1, P2, P3 and P4. Okay, and this whole Gunicon will be accessible. This is -b means binding. So I can access all of these processes and this whole app.run. I can access it on 127.0.0.1 on port 4000. And what is it that I want to run? WSGI app. Okay, what I want to run here is WSGI app. Now the moment you execute this command, look at this, the moment you execute this command now, let me just show you on the terminal. Control R. 1 second. Okay, so the moment you execute this, look at what it says. It says I'm starting Gunicon and I'm listening for requests on this server. Look at this. I'm waiting for requests on HTTP on this 127.0.0.1 on port 4000, and this is my process ID. This is the parent process ID where Gunicon itself is running. And it created 4 processes. Look at these 4 lines now. Look at these 4 processes. It said I am starting or I'm booting a worker whose process ID is this. I'm creating another worker here. I'm creating another worker here. I'm creating another worker here. Now, even if 100 people, now imagine if I get a flood of requests. Okay, imagine a situation where, let's assume, okay, let me use the previous diagram here. Okay, so suppose imagine I have 100 clients here who are saying, okay, this is my X1, this is my X2, please give me Y1, please give me Y2, Y3, etc. My Gunicon is sitting here, right? It will take all these requests and it will use these 4 processes to send back YIs. Okay, so this is one way that you can use parallelization in the production environment. Okay, again, lot of stuff that you want to do is handled by your WSGIs. Okay, like Gunicon. Again, there are other alternatives also. So if you go to Flash official documentation, so Flash deployment, sorry, Flask. Okay, so look at this. So there again, these are the deployment. This is official documentation of Flask. They say how you can deploy it on Heroku or Google App Engine or AWS or Azure, right? Or if you want to use Gunicon or other types of WSGI containers, there is a lot of documentation here. Okay, so what we covered is how to use Gunicon as one of the WSGI HTTP servers that we can use for parallelly executing this. Again, I've taken the command from here itself, right? So it's the same command, 4 workers, right? And this is the IP address and the port that is bound to this, to the Gunicon job and things like that. Okay. So yeah, so this is what I wanted to cover today. Again, we just got it under 90 minutes. So I'll go into the, okay, let me give a second. Okay, I'll go into the chat window and I'll try to answer as many questions as possible from now. Okay, cool. Let's get into it. Okay, so Biju, good question. Your question here is, isn't it same as load balancing? It's not. So there is so a lot of people, load balancing is a concept in distributed systems. A lot of people use Gunicon with Flask APIs with Nginx. Okay, Nginx is spelled as Nginx. Nginx is often used as a load balancer. Okay, so a load balancer tries to balance between multiple computers also. So here Gunicon is only working like a web server interface. It's not a full-fledged load balancer. Okay, so if you want, you can use a full-fledged load balancer. Again, there are multiple load balancers, Nginx being one of the popular options, which is often used. So in some of the other documents that you can see in the Flask official documentation, people do use Nginx. That's again, that we are going into more software engineering, distributed computers, distributed computing and things like that. That's why I didn't want to go into it. Let's focus just on the parallel computing part of it. Okay, cool. So Abhijit has a good question. Why don't we use Dask? Yes, Dask is a very popular up and coming system. I'm not in favor of any one system or other system. Okay, Dask is a much more low level API. Dask is also getting very, very popular. But the problem with Dask is this. So if I have to choose between Dask and Spark, I would actually use Spark. And the reason being, Spark is much more mature. Spark has been used in the industry at much larger scale. I have personally used it both at Applied AI course and in my previous company Amazon at fairly large amounts of data. To crunch data, we use Spark extensively, right? Even to build some simple machine learning models, we do use Spark. So Spark is much more thoroughly tested. Dask is a good system, no doubts about it. I think Dask will become very popular, could become, I'm not saying will always, but could become very popular in the future. You can use Dask also. So it's just a call. Okay, so probably if time permits, we can do one session on the internals of Dask. Okay, so is CUDA used in machine learning? Yes, yes, yes. So when I say GPU programming, we're talking about CUDA. Again, for those of you who don't know what CUDA is basically like a bunch of functions. It's basically a library that is released by NVIDIA to do parallel processing on their GPUs. So whether you take TensorFlow, you take PyTorch, Keras, all of them, whatever code you write gets converted into CUDA code. Yes, CUDA is used extensively in deep learning. It is also used in machine learning. For example, using TensorFlow, you can train a logistic regression model, a linear regression model, a linear SVM model. All of that you can train, right? Right. So yes, it is used. When we have, so Trojan has a question, which is when we have submatrix inside our data matrix, how do we fit them inside our box? I mean, we have dedicated memory, but what if they overflow? Trojan, that's what I said, right, in my discussion. If let's assume your data is so large that it doesn't fit into your RAM, then can you run your algorithm? Again, most modern libraries, what they'll do here is they'll get chunks of data from your disk to RAM, process that, throw it out of the RAM, again get another chunk of data. That's how they process it internally. Most libraries do that already for you. But if it will take more time, because writing and reading from disk takes more time, right? Reading from disk to RAM is very slow. Even if you're using SSDs, it's quite slow compared to reading from RAM or reading from cache. So what happens very often is, in such a situation, if you have very large amount of data, for example, we have a case study where we process, I think, close to 100 GB of data. We have one of the case studies that we do as part of the course videos. This is Microsoft malware detection. That data will never fit into our RAM, but we discuss about how to tackle such problems. It will take time. You have to be patient there. If you have only one computer at your disposal, you have to be patient, but it can be processed. By copying chunks of data into your RAM, processing it, letting it go, again copy one more chunk into your RAM, processing it, letting it go, and so on and so forth. That's one approach. Or if you have multiple computers, just go use Spark, right? So very simple. Okay, somebody has a question. What should I do to teach my friends? Simple. I mean, I became better. I was a public speaker when I was a student in school days. I enjoyed public speaking. So I think some of my teaching and in general explanation abilities were built then. But my suggestion to you is this: if you want to teach, one of the things that I learned from Andrew Ng, I mean, this is a very nice video from Andrew Ng, is he says when he first joined Stanford, he was not a very good teacher. He was rated one of the worst teachers in the computer science department. But then he said, okay, I'll take a topic, I will record myself, or I'll look at a mirror, teach a concept for 10 minutes. And he consistently improved that. He saw his own video and he said, hey, I'm not teaching correctly. He would again reteach, he would reteach. So he would criticize his own videos, either using a mirror or using a video recorder, and he improved within 1 to 2 years in being a very good teacher. That's one. The second thing that I would recommend here is teaching requires patience. Teaching requires you to put yourself in the shoes of the learner, right? And thinking from the learner's perspective. This is a skill that I learned over the last few years. I didn't know this skill earlier. Okay, very simple tricks. So Sarvesh, your question here is there any online solution where we can preload data needed to process something like Redis and Crunch more quickly? Look at this. You can use any distributed system, dude. See, suppose you have Redis. What is Redis at the end of the day? It's a distributed key value store. That's what it is, right? At the end of the day, that's what it is. It is a distributed hash table. Okay, of course, it has redundancy, it has all the other fancy things. But bottom line, it's a distributed dictionary, which means you have, let's assume you have 10 boxes, box 1, box 2, box 3. So this dictionary is being stored in the memory of all these 10 computers. You're going to read from that. That's all. You still have compute as your bottleneck, right? Each of these computers still have only a few number of cores. How you store your data? See, what Redis does is, Redis enables you to be able to quickly query the data because it's stored in a distributed hash table. But at the end of the day, all the compute equation updates have to be run on your cores, right? Redis can't speed that up. Redis can only speed up access to data in a distributed fashion, right? So some people in Spark environments, again, Redis is designed for a distributed computing, not for a parallel computing like approach. If it's a parallel computing approach, I can store the dictionary using standard dictionaries in Python, right? Why do I need Redis? If it's a single box, why do I need Redis? I just have dictionary in Python inbuilt, right? So in a distributed systems environment, yes. Like for example, if you have Spark, you can fetch the data into RAM using Redis. But again, that seems a little overkill because the RDDs in Spark, as we have discussed in the previous live sessions, RDDs in Spark are distributed memory units, and Spark has optimized them enormously for speed, right? Cool. Can Julia also perform all ML functions you mentioned? Again, I'm not an expert in Julia. I don't want to comment about it. But languages like Julia, Go, etc., they're still not mainstream, to be honest with you. The easiest language to build machine learning systems today is Python, because there are so many libraries available for it. It's as simple as that. You can write in Julia. I'm not saying you shouldn't. I've written code in C also earlier. but the libraries that are available are too few, so you'll have to implement a lot of stuff from scratch. Okay. Cool. So what else? Okay, I think there are some questions from earlier that I missed. So I'll go up and answer a few questions from there. TensorFlow developer certification from Google will help my resume to stand out. Again, if you have bandwidth, if you have time, if you have resources, go ahead, do it. So right now, one of the problems here is some of these cloud certificates are useful. For example, the Google TensorFlow developer certificate, I think it will certainly add some value to your resume, but the effort that you need to put in and the price for the examination is non-trivial. So you'll have to take all of that into account. Okay, so feel free to do it. Okay. Can we use Spark for reading IO operation instead of multi-threading? Again, I think many of you are getting confused between multi-threaded or parallel code with Spark code. So we have done a other session. It's publicly available. The first Spark session is publicly available on our YouTube channel. Feel free to check it out, where we discuss how Spark fits in. Remember, Spark also internally. See, Spark uses data. Spark splits the data on multiple computers. On each computer, it uses the multiple processes and multiple cores and multiple threads internally. It does that already, right? Spark typically kicks in when you have large amounts of data that you can't store on one computer, either on disk or on RAM. Okay, that's where Spark kicks in. So Spark falls into the distributed systems model, but Spark internally uses multiprocessing, multi-threading, all of that. Okay, so you should check out that other live session. It's a 2-hour live session about the basics of Spark and Hadoop, the architecture of Spark and Hadoop. So please check it out so that you can understand that better. Yes, Parikshit says, doesn't NumPy use some of this parallelization? Yes, it does. So when you write, very simple example, right? Imagine you're writing some matrix multiplication on your own. Okay, some for loop, so triple for loop thing that you can write, right, for matrix multiplication. The code that you write is going to be much slower than actual Python, NumPy's multiplication. Why is it so? Because NumPy's internal implementation is written in C. So it will run much faster than your Python code, number one. Number two, it also leverages the multiprocessing and multi-threading capabilities. That's why whenever possible, if you want fast execution, use NumPy's internal functions, because they're very beautifully implemented. Right? So some of it is implemented. The reason I went into the mathematical details is because understanding the foundational skills is important. Many people don't realize it, unfortunately. People say, hey, I know this library. So that's why if you look at most top product-based companies, they don't ask you, hey, do you know that tool? Do you know this tool? They'll say, tell me, how does this work internally? Like, I've been in interviews of senior engineers and managers, and people say, I've used Redis. Okay, explain me, how does Redis handle this situation? Because I want to understand whether that person understands Redis's internal architecture. Because in our team, we use Redis and Memcache. We used Redis and Memcache. So what is important is a deeper understanding. What is happening under the hood? Again, otherwise people can say, hey, I know how to write TensorFlow code, I know deep learning. No, you don't know. You know how to write TensorFlow code, you don't know deep learning, right? So to understand deep learning, you have to understand the underlying math, how TensorFlow optimizes things internally. So if you want to be a good engineer or a good data scientist or a good machine learning scientist, or in general, a good engineer in general, try to grow below the hood and understand what's happening. Because that way, your depth of skills are better, you know which tool to use where. Okay. I could have finished this session by saying, hey, NumPy has this distributed stuff. Again, I wanted to show you how to implement a Gunicon-like system from scratch, but that would take 2 to maybe even 4 hours. We can implement a Gunicon-like system ourselves, by the way. It's not impossible. We can implement it from scratch by using the basic functions of basic functionality of Python. But I said, okay, most people will end up anyway using Gunicon in production, so let's talk about it. If you are a software engineer, it's a very good exercise to say how Gunicon works internally. Okay, or how let's say CUDA works internally. Okay, so those are interesting. So always try to go one level deeper, if you can, multiple levels deeper, so that you get a deeper understanding of the concept and you have a better appreciation, better applicative stuff. Now I know what to apply where, right? Suppose imagine there's a new distributed systems platform that comes up. Let's assume Kafka. It's not very difficult to learn because my foundations of computer science, my foundations of distributed computing, my foundations of machine learning, my foundations of data structures and algorithms are strong enough that I can pick up Kafka in no time. Because at the end of the day, it has to use basic data structures, algorithms, distributed computing concepts, right? It doesn't invent anything new. It probably optimizes some of these things. So having strong foundations, either mathematical, data structures, algorithms, computer networks, all these are very, very useful. For example, whole of multiprocessing and multi-threading, right? It's taught to computer science students in operating system subject. I mean, if you're a computer science student, if you've done BTech in computer science, you should know all of operating systems. You should be able to implement something like Gunicon in like a weekend. Because you know basics of computer networks, you know basics of operating systems, right? But unfortunately, most people don't learn that, which is unfortunate. But again, knowing that foundations are important. Okay, so can you implement logistic regression, machine learning using C++? Yes, Manoj, you can. Again, one of our assignments in the course videos is to implement linear regression with regularization in Python. You can certainly implement it in C++, and the code that you write in C++ could be faster. But the only problem is this. The amount of time it takes to implement a C++ code, because remember, C and C++ doesn't have garbage collection, which means you have to take care of that. You have to do memory stuff. You're re-implementing everything that is implemented by NumPy and scikit-learn to some extent. Probably your code could be faster than scikit-learn also. Again, in my previous work experience, we have implemented things like logistic regression or graded boosted decision trees using multiple cores in C++, which is way faster than most Python libraries. We've implemented it from scratch because that was a production environment where we needed like speed. The difference between, we didn't even use Java. We wrote code in C and C++. Okay, because speed was critical there. Unless speed is critical for your applications, there's no point doing it. Okay, if you want ease of use, Python is much better. Scikit-learn, XGBoost, all these are pretty good. But if you want speed in productionization, you have to do it in C++. Okay. My Python executable produces predictions for multiple time series in parallel, but the program gets stuck at some point. Have you encountered this behavior? One second. Your Python executable produces predictions for multiple series in parallel, but the program gets stuck at some point. Avnish, again, debugging parallel programs can be a little tricky, but probably what's happening in your system is it's getting into a deadlock-like situation, where one process is waiting for other process to complete, other process is waiting for another process to complete. If there is any such dependency like structure, probably that could be one case that could be happening in something like that. Again, just put in tons of debug commands and debug it slowly. Again, I understand that debugging parallel code can be a nightmare because keeping track of, okay, what process till where it is run, what process till where it is run can be a nightmarish situation. But you can do it using either the Python debugger or just print debug commands. Print log everything so that you can go through the log commands, all the output, and see why things are getting stuck. One reason could be a deadlock like situation. Okay, cool. Can you briefly touch upon how to build Gunicon like system using Python? So look at what is Gunicon doing. Okay, it's taking HTTP requests. Okay, it's taking HTTP requests and then it creates a pool of processes, and whenever a request comes, it's adding it to a queue. Okay, suppose you're getting a request. So let's assume you're getting requests. The Gunicon system takes the request, adds it into a queue. It has a bunch of it has a pool of processes. It assigns them to each of them and it returns the output, right? So effectively you can build this system using Flask, using a queue, and using a pool of processes. Again, you may not be able to build all the functionality, the full-scale functionality of Gunicon, but all you need is basically a pool of processes, a first in, first out queue, a queue data structure which is inbuilt in Python. Python has a queue implementation, and a system that can take all these requests. So again, you can take web requests using web APIs, right? So you can build a Flask API which takes these web requests, stores them into a queue, and it also has a pool of processes. It will assign each of these requests to a pool. As soon as the process returns back, it sends the response back. A little bit of orchestration needs to be done, but it can be implemented over a weekend. Okay. So somebody's heretic says between VS Code and PyCharm, which is the best IDE? I don't use either of these IDEs. I use Vim. I mean, I'm being honest. I mean, I've used Vim all my life. It's one of my favorite IDEs. I've used Atom. So there is Atom also on my computer, which I've used a few times. But like IDEs are like t-shirts. Okay. I like this t-shirt. You might like another t-shirt, or it's like hairstyles. Everybody has their favorite. Okay. My favorite is Vim because I'd like to go into the production system, log into the production system, just look at the code, change it there. Like I like Vim because it's bare bones. And I've been using it for 15 years now. So Vim is my favorite editor, but everybody has their favorite editors. I don't have a favorite except Vim. Okay. Did someone finish all the course material first and finished all the assignments later and showed up at a good company with great package? Abhishek, I mean, so what we recommend, again, there are some students like that, okay, to answer your question to the point. Some students finish all the content, then start the assignments. But we don't recommend that. We recommend you do the assignments in parallel. So for example, you can assign your weekends. I mean, one suggested strategy is this. Throughout the week, you're learning a bunch of concepts. Weekend, do an assignment. If you want to spend the whole 2 days to do the assignment, that's perfectly okay. Because this assignment is connected to the concepts that you learned through the week. Think about it that way, right? Think about, I mean, that's a much easier way to think. 5 days you learn, let's say you spend 2 hours a day, 10 hours of content you learned. Do the assignment. Okay, even if you learn 5 hours of content, you can finish the assignment. So this assignment can be thought of as a revision of the concept you learned in the week, right? Before you move on to the next topic. That's what we recommend. Okay. Janardhan has a question. I'm working on a feature engineering for my final case study at Applied AI course. Good. Okay. My dataset is 5 GB and increasing. I have 2 boxes with 12 and 32 GB boxes. Will Spark be an option? Don't use Spark, man. Come on. You already have a 12 GB box. Why bother about it? See, Spark should only kick in when you have something like a few hundreds of GB of data or maybe a terabyte of data. Otherwise, Spark becomes an overkill. Okay. Okay, so Prakhar, sorry, it's again a tongue twister. Prakhar says, is it sensible to pursue Applied AI course while doing MTech from IIT? We have hundreds of students from IITs and IISc and other top research institutes across the world who take Applied AI course. The reason they do it is as follows. I mean, I have friends of mine from IISc who have graduated 10 years back who are taking some of these courses now. The reason is as follows. Most IITs and IISc teach you the theoretical parts very well. They focus on a lot of mathematical stuff. They do that very well. They focus also a lot on research. What they lack is the applicative details. So a lot of students at IITs and IISc, they take our course primarily to learn how to apply all the theory that they are learning into real world stuff. Again, when I was a student at Indian Institute of Science, which is one of the best universities for machine learning in India, for sure, hands down, I learned a lot of theory. I didn't learn any applied stuff, to be honest with you. I mean, I have huge respect for my professor. I learned a lot of beautiful theory. I was doing beautiful mathematics, but I didn't learn how to apply these things to real world. It is in the industry that I learned it. So I had a lot of mentors in the industry who helped me, who nurtured me over the years. Through their help, I learned how to apply all this beautiful math to real world problem solving. Okay. Okay, cool. How do I install Vim editor? Vim comes in terminal, right? Linux terminal has Vim. Like, I think, I don't know about Windows, but I think Windows also has Vim, right? So I think it should be simple to install. Like, I've been using Linux and Mac computers for the last 15, almost 20 years now. And I had Vim inbuilt almost, right? So I don't know. Windows also, I think it should be straightforward. There should be a Vim installer. Can you suggest any one Docker container that includes multiple deep learning, machine learning libraries? I don't know exactly. I've used it, but some of these Dockers, I would write the Docker config file myself and install these things. But I'm sure if you Google search for it, you should be able to get it. It shouldn't be so hard, I feel. Okay. Okay, cool. Yeah, I think I've answered most of the questions. Again, I'm trying to answer as many as possible. Can JavaScript be used for machine learning? It's a good question. Yes, you can. So if you want to do some really interesting stuff, there is something called TensorFlow.js. I really love that. Okay. Yes, there are people who have built machine learning systems in JavaScript so that they can run these models on the client end, which means on your browser. Instead of running these models on the server, they would run it on the client. So TensorFlow.js is very, I love that tool, because all the TensorFlow models that you build, you can execute them on the client browser. So we have some TensorFlow.js systems that we built for video analysis, for face tracking and things like that. So we at Applied AI course have used it extensively. So we conduct these tests regularly, right? So where there are some video questions, there are some multiple choice questions and things like that, and we track so as to avoid cheating. These are primarily for self-assessment of students, and we use TensorFlow.js to see where the person is looking at, is there a abnormal behavior, cheating or anything like that. So it's a cool tool that we really enjoyed using. Okay, cool. Okay. So somebody says if somebody wants to mix gaming and machine learning. Again, machine learning and deep learning in gaming is used primarily to design smart agents, where reinforcement learning is used. Okay, that's one of the biggest applications. Okay, again, that's one space that you can look at. Okay, so between Python and R, I would choose Python any day. I've used R also. R is a beautiful tool for some advanced statistics functionality, but I mostly use Python because it's much easier. Productionizing Python code is easier than R code. So we prefer, that's why we teach Python and not R. R has its own applications, but if you look at the in general market, Python has much higher lead because much more stuff can be done in Python. Okay, R, surely if you want to do some advanced statistics stuff, R is certainly useful. You can pick anything, but I would pick Python any day. Okay, cool. So how can we connect the theoretical concepts when building ML models rather than treating them as black boxes? Again, Saiteja, the logic there is, suppose you're training a model, right? Ask yourself, suppose you got some weights. Try to interpret the weights from a geometric standpoint. Okay, suppose you're doing a simple logistic regression or linear regression. You have a hyperplane. Now, in multiple trainings of the hyperplane, is the hyperplane changing a lot? Okay, which means there is a lot of, the model itself is not robust. Okay, so always think of, whenever you're training a model, don't think of it in terms of scikit-learn's function. Think about it from the loss function's perspective. Ask yourself, on this data, what is happening with the loss function? What is happening with the regularizer? What is happening with the constraints if you're training something like an SVM, right? So again, code is important. I'm not denying that fact. But thinking from a code front is not very helpful. Thinking from, again, even when you write code, right, look at each of the hyperparameters and always try to connect it to the underlying mathematics or geometry. Again, that's something that we strongly recommend our students do. That's something that I do every day. Whenever I'm training a model, I think from, okay, see, code is only a way to express what you want to do, right? But the thinking part should not be from code. Thinking should be, okay, I'm writing this function. What is it doing underneath? How does the loss function look like? What is happening with the regularizer, right? Or what is happening with this plane? Okay, so that's a better way to think about it. That's a thinking process that you can build slowly by connecting whenever you're solving a problem, think from the geometry perspective, think from the mathematical equations perspective, and not from the code. Code is only a means to get a numerical solution. Okay. Okay. What do you think about market mix modeling? Is it a data science problem? Again, market mix problems have existed. They have been solved mostly by statisticians, and they've been there even before modern data science. Okay, so you can pose them as data science problems. I've seen people who pose it as data science problems, but a much better way to pose market mix models is think about it like an optimization problem. Okay, that's what it is, right? At its core, a market mix model is basically an optimization problem that you're solving. You want to determine where to allocate how many resources, right? Or where to allocate how much money. So instead of thinking it as a data science problem, it is better to think about an optimization problem. And remember that optimization is core to a lot of machine learning also, right? So optimization is this beautiful area of mathematics which is used by operations research, by supply chain management, by market mix modeling, by tons of people, including machine learning guys. Okay, cool. Is Google Pro available, Google Colab Pro available in India? I don't think so. I tried to get one for myself. I couldn't get it. So I'm just using the regular Google Colab. I think it's only available in the US. It's not available in India, right? So somebody says how to conduct competitive programming problems. Yeah, so we are thinking of some of these things. So probably in the near future, we'll do a session on how to solve dynamic programming problems. We'll try to do that. Okay, so we'll surely do that. Or how to think when you're doing a competitive programming problem, how to think. It's not about exactly, oh, this problem, this is the solution. But we thought we'll do a session on how to think or how some people think, okay, when they have to solve a competitive programming problem. Okay. So somebody says applied blockchain course, we are not doing it anytime soon. So not now. It's not on our horizon for sure. Okay. Cool. Sounds good. Thank you, folks. Thank you for attending the session. And again, we'll announce the next live session for the next week. Thank you once again for joining the session. I hope some of you have learned some concepts. I will share the notes of the discussion with all the reference links in the description section of this video in the next few minutes. Okay. See you. Thank you very much. Have a good weekend. Bye-bye.